Uh, so hi everyone. This is mainly just a like sort of not a very brief but a recap of the ES335 course machine learning, and yeah, let's just get started. So this is only till exam one. I think I'll make a second part once the whole course is over. But let's just start. So uh, yeah, so we're just gonna skip the introduction completely because I'm assuming that most of you know what the whole thing is. But essentially, in traditional programming, you give rules and data and then you get answers. But in machine learning, you do the exact opposite. So, uh, traditional programming, right? What you do is you give rules and then you also give the data, and from that you get the answers. In machine learning, it's very different. So in ML, what you do is that you give the data and you give the answers, and your program gives you the rules. So uh, right, next thing. So once again, just some notations. Usually the data set is given as a matrix capital X, where this matrix is essentially just a collection of vectors which are row vectors. So you will have vector x1, x2, so on, and these vectors, they are numbers which characterize a certain event essentially. So the columns of this capital X matrix are called like features, because what features characterize an event, that's the thing. And anyway, the answers, so that's just the data. The answers are essentially this matrix Y, which is once again a column vector. And now these are just some, it could be a whole matrix if you want it, but in any case it's just something that's once again sort of like this capital X thing, except these are our targets, as in this is what we want to predict. Right, so those are just some notations that we're using throughout. Okay, let's get right into it. So first, some actually let's just, yeah, whatever, let's go for some more terminology first. So there are two sorts of like basic programs that you could write. One is a classification program and one is a regression program. And whenever we say program, this is like synonymous with a model, as in a model basically does all of this stuff. It takes in data, answers, and it gives us rules, and can also do the opposite, as in it can take the data and can apply those rules to get the answers. So for example, you could have a model like y equal to mx plus c. So you give it different data points, right? And then it will sort of try to predict, you know, what like the parameters should be, and it will fit these parameters. So the model basically trains on some data set. So our data set in this case is like just this capital X matrix, which is like this thing, x1 1, x2 1, so on. And then this y vector, so just y1, y2, so on. And essentially your model is like you just do this times of this vector mc, and that should give you approximately this thing. So whichever one gives us the best approximation, like whichever mc gives us the best approximation, that's the optimum parameters for our model. And so the way we find is using visually gradient descent, but in this case, this is what we are doing is just linear regression, which we'll learn about later. So okay, so that's what a model is essentially. It's just some way to estimate the answers given the data, and then we try to change the variables, so MNC in this case, such that our estimate becomes better and better as a whole, not just for one particular data point, but in general it becomes better. In this particular case, the thing we do is that we try to minimize this. So we also call this MC vector as theta sometimes. So just we try to minimize these the Frobenius norm. Actually, let's not do the Frobenius norm. This is a vector, right? So it's a vector in this particular case. So we'll just try to minimize this thing. Y minus x theta, that vector, the magnitude of that, of course, the Euclidean norm squared, right? That is to say, we are trying to minimize the summation of I minus minus mxi minus c squared. So we minimize this by obviously like taking the gradient with respect to m and c and then setting it equal to 0, but it could have also been done by gradient descent, which we'll learn about later. So yeah, um, so this was particularly a regression model. You also have things like classification model. So in this case what we did was we give it some continuous data and we expect some continuous output out of it, which approximates the value of some certain thing. Now what if instead of approximating you want to classify whether or not something is of a particular type? So for example, the classic way of explaining this is using the MNIST data set, where you have um, you know handwritten digits. So maybe like, okay, so I'm just gonna, yeah, it probably shouldn't be drawings. So maybe you have this handwritten digit 6, which is actually like very pixelated and it's not as smooth as it appears. So it's like 256 pixel thing. So this is like 64 cross 64 sometimes. Yeah, so this is like an image, and using these 256 pixels you want to predict what this number actually is. So as in you will give it that image and the model should give us 6, something like that, right? And so you will do this for many different images from for the numbers 0 till 9, right? And so then the model is basically like this, that so I'm just gonna abstractly write model and not specify what are we exactly doing, but you give it an image which just, I don't know, just draw it. You give it an image which is like 256 pixels, and that gives you one particular number, right? So maybe a 6 or maybe a 7 or maybe an 8 or whatever. So let's just call that target as t. Sorry, let's just call this number as y prediction, and then you compute the loss with respect to y, right? So you can compute the loss and you try to minimize this loss, and this is obviously done using gradient descent, like you back propagate all that stuff, but we'll learn about it later essentially. But yeah, so your model is fitted in a way such that this loss is minimized. Usually this loss is like the cross entropy or something, but let's just not care about that right now. Okay, cool. So that's classification versus regression. Now let's get to some metrics which basically tell us how good did a model do. So for regression, the usual metric that we use is something called the mean square error. Now what is the squared error? Or before the square error there is something called, so okay, let's just actually start. So let's just go back to a linear regression model. So linear regression is once again just a regression, as in we are trying to approximate values of a continuous variable depend on some other variables, right? And we are expecting that relationship to be sort of linear, as in you might be given some data points, different xy values, and then you want to fit a line. So that's just in one dimension, as in you have one free variable and one dependent variable. You could have multiple free variables and one dependent variables, and that would be something like an n-dimensional linear regression. So let's not go too deep into that, and just think about it. What should be the metric for linear regression? So let's say that each value of the dependent variable can be written as approximately, or let's just not do that. Let's write the error term explicitly. Can be written as so some vector theta transpose. So I'm writing transpose, but if you want to think of it more in a physics perspective, then it's like theta dot whatever. It's not exactly physics perspective, but you get it, right? It's used in physics a lot, this notation. So theta vector dotted with the xi vector. So this is just a list of all the features values for that particular event, and then maybe some error term associated. So this is like how far off is this model from the actual what like happened, right? And so if these errors are having a Gaussian distribution, right? So then we can say that the probability of what was I going to say? Yeah, so these are probably going to have a Gaussian distribution, right? Yeah, I mean, we can just say that maybe EI or maybe E in general just is like it's normal with some mean 0 obviously, because yeah, and then some deviation sigma square, right? So that's one thing. And let's just say that all of these errors are independent. So E1 is independent. So probability that E1 equal to maybe some capital E1 and then E2 equal to capital E2. This probability is exactly probability of E1 equal to capital E1 and E2 and that times the probability of, and that times the probability that E2 is equal to capital E2. So something like that, right? That's saying that these errors are independent of each other. And there's a reason why we're dealing with the Gaussian distribution here, but just run along with that for now. So if that happens, then we want to find the best theta such that the so firstly just figure out what the probability of what was I going to say? Yeah, right. So what's the probability of the errors being a particular value? Let's just say capital E, right? So what's the probability that that's the case, right? That's obviously the probability that the first value is that, and so on. So like we're just actually going to write it as a product. So product from vi equal to 1 till n of so there's a normal distribution, right? So just e power minus x square by 2 sigma square, and then there's some constant factor, so I'm just going to call that constant factor as capital C. We don't really care about that. It's minus x square upon 2 sigma square. Okay, I shouldn't say it like that. Minus ei square upon 2 sigma square, right? So that's the probability of a particular error being there, right? Now ei is essentially just y minus theta x, right? So yi minus theta, there's no I over there, so theta dot x I, right? That thing, norm of that, not the norm actually, because it's just a scalar at this point. So that thing squared upon 2 sigma square, right? So that's the probability of your errors being the way they are. Yeah, so essentially right, so essentially like what we're saying is that if your yi was supposed to be like that, but then it deviated by ei a bit, then what's the probability that it did in fact deviate by that error? As in, there's a bit more, this is like supposed to be a bit more deeper than that, but essentially we're doing some Bayesian probability thing, but we don't have to go too deep into that. The likelihood is in fact, and yes, this is actually a technical term, the likelihood is actually given by this thing, right? So this, I should actually write the probability of this error given that this model is correct. So given the vector theta, right? This should also be vector, right? So that's, yeah, that's our likelihood of our theta being correct, right? So the total thing, the posterior probability would actually be like probability of theta being given the error. So is, if the errors were correct, then what's the likelihood that theta is the way it is? And that would essentially just be probability of e vector theta, okay, given in terms of probability of theta vector upon the probability of e vector, right? But then this term is sort of something that we have to assume. This term is once again something that we sort of assume, and so what we can do is just like say that, oh, these are some constants, like doesn't depend on theta all that much. So in that case, essentially like maximizing this is the same thing as maximizing this thing. And so yeah, we just maximize the likelihood. Now how do we maximize the likelihood? Essentially we want to maximize the natural log of the likelihood. So just natural log of this whole thing, so it's like some natural log of c, just call it small c, plus the summation of, so if I equal to 1 to n, the summation of this stuff, so just actually put a negative over there because that's a negative over there, minus 1 upon 2 sigma square yi minus theta vector dot x. So we want to maximize this thing, but that's the same thing as minimizing this term. And guess what this term is? This is called the sum of squared errors. Yes, a very intuitive name, but essentially minimizing this is the same thing as minimizing this term, 1 upon n summation I equal to 1 to n of yi minus theta dot xi, right? And this thing is called the mean square error because it's the mean of the squared errors, obviously. So this is something that's used as a metric for telling how bad did our model predict, right? Right, cool. So yeah, this was a bit too mathematical for no reason, but I just had to say all of this. So yeah, now we have at least one metric for regression. So I'm just gonna say regression metrics. So regression metrics. So we essentially use the mean square error. Not, you might say, why not the SSE, right? The sum of squared errors. The problem is SSE scales up with the data set, right? So the more data you give, the bigger the SSE will be, and that doesn't make sense, because say that you predicted on a smaller data set, and you predicted like really really bad, and the mean square error is like very high, and then you predict it on a bigger data set and the mean square error is pretty low. It could still be that this guy has a lower SSE and this guy has a way bigger SSE, just because of the fact that this is a very big data set. And so it doesn't make sense to be using SSE as a metric for, well, how good did your model do. What you should be using is the MSE. Okay, so that's, oops, I shouldn't have done that. So that's essentially the only regression metric that you will be actually using, because yeah. And coming back to why did we assume that the errors are normal in, so are actually having like a normal distribution. So what I like, so the explanation that I like is, let's say that these yi values were supposed to be maybe like measurements, right? Yeah. This is probably not a good way. Yeah, okay, right, whatever. So maybe like you were doing something like V equal to IR or something, right? And then you only have values for voltage and current, and you want to predict what this resistance is going to be, right? You're doing some experiment, but your measurements aren't exactly accurate, right? So you sometimes get small errors. So then what you'll have to say is like V plus some error term, which is something which is following a normal distribution. Why is it following a normal distribution? Central limit theorem. I won't explain further. You just have to and like trust me on that. And the actual current value plus something that's following a normal distribution again. And this is like sigma 1 square, sigma 2 square. We don't even know what this is actually. Length of R. So doing all of the like probability stuff, what you essentially get is like V equal to IR plus something that is following a normal distribution with some sigma square, and the mean is certainly 0, right? Yeah. Right, so that's like the justification for why do we assume that these errors are in fact a normal are like following the Gaussian distribution. Okay, so that's like one regression metric, and the only regression metric that we really care about. Let's go to some classification metrics. So yeah, firstly, before classification matrix, let's start to understand something called entropy. Yes, I have been waiting quite a bit for telling about this stuff, but this is going to be fun. So how do I start this? So let's just start with the basics. Let's start with Hamming codes. So suppose you are given how do I say this though? Okay, suppose you are given some big text paragraph, right? Something, I don't know. There's like a lot of text written over there, and you want to compress this text into something of a smaller size, right? Some file format of a smaller size. How do you do that? The best way essentially is to be using something that's called there's a prefix code called Hamming code. And so what it does is that it assigns each character, so this is a character, this is a character, so on. It assigns each character a variable length encoding. So maybe this is like 0 0, maybe this thing is something like 0 1, and maybe this thing is something like, I don't know, 1 0 0, whatever. So it assigns it different uh, encoding, right? And it does it such that the ones with the biggest frequency, so the characters, maybe this is A, so A has a very big frequency, that's given the least value, the least length, sorry. And so whenever you want to compress something, this is probably the one of the major ideas that you could use, that you can compress it by assigning each character encoding based on their frequency, right? And another way of saying frequency is more like probability, right? Yeah. So whichever one has the biggest probability is assigned the least length. And how much less length, that's sort of like natural log of 1 upon pi times some constant factors. Maybe like there's some constant c over there. This is like, this constant factor is like dependent on the size of the string that you're trying to compress, but well, whatever, we don't really care. So essentially just negative natural log of pi, this is a this is like a number that's proportional to the length of or maybe like some factor something minus natural log of pi, but whatever. This is something that is linearly related, that's a better way of saying it, to the what was I going to say, to the length of each character, right? And so let's try to figure out what would be the length of our new file, right? So that's just going to be the expected, not the expected, what should I say, that's just going to be the total number of bits, right? Now how do you figure out total number of bits? So just say, well, figure out the total number of characters over here. Let's say that those are like n, so n times of pi, that's the number of characters for a particular character, okay, number of instances for a particular character. And then so that times the length of each of these, which is in this case like linearly related to this quantity. And so you just sum this up for each of these characters, right? And yes, it's linearly related to this thing. There's some constant factor over here, but we'll completely disregard that and we'll just not care about that for now. Because I don't want to be getting into too much details. But yeah, so this is sort of, yeah, so this is like sort of an approximation for, yes, so this thing is by the way an approximation. You shouldn't be taking this too seriously. And also you don't use natural log everywhere, you actually use log base 2, but who cares, I'm just going to use natural log for this particular case. So yeah, whatever, you just, what you want to do is essentially you want to minimize this quantity, and in that way this whole quantity is also minimized, right? Yeah. And so now this negative log pi thing is called the self information, for good reason obviously, because this is like how much information is sort of needed to express this, or maybe something like that, but I don't know, for some reason it's called self information. It's coming from information theory, and I actually don't have a very good idea about that stuff. But anyway, so this thing divided by n would be the expected number of bits required to send a message of unit length, right? And so this is essentially the information that is contained in this string, right? So if you like remove all the redundancies, just boil it down to the basics, the minimal length, then this is the expected length of each character's encoding, essentially. And so this thing is given a rather nice name. It's called the entropy. Okay, not this thing actually. Yeah, right. Okay, whatever. So yeah, let's just go with this thing. So it is called the entropy, which I'll denote as capital S. A lot of times it's denoted as capital H in computer science, but since I'm studying statistical physics, for some reason I just like this S notation better. But yeah, so this is called the entropy, and it's like given by negative summation of, so summation over I of pi natural log of pi. Actually, this is not quite the case. In case of physics, this is actually the case, that you multiply it by the Boltzmann constant. But we're in computer science right now, so we won't care about this. And over here you should now be having a log base 2, because once again computer science. So log base 2 of pi. Now from there you can define another quantity called the information. And the information is essentially like what's the worst case entropy, like the biggest entropy that you could have? Well, that essentially happens when each of these pi values are exactly the same, right? And in that case, each of these characters would just be needing the same number of bits, because you cannot do that whole give less number of bits to the one with bigger frequency thing. So let's just say that the number of characters are maybe something like, I don't know, there are like m characters. Cool. And so the number of bits required for each character would just be log, so log base 2, log of m, right? And so the expected, yeah, okay, that's actually the number of characters, so that's pretty much it. So yeah, this is the maximum sort of entropy, if that makes sense. Okay, something is weird over there. No, okay, that's actually right. So if each of the pi's are just equal, then this whole thing just becomes negative summation log of 1 upon m, which is in fact just log of m. So that's like expected value. So what we sort of want is the difference between the worst case and the best. I'm saying it's the best case, but it's more like an approximation for the best case, so just kind of take everything with a brick of salt. So that's called the information. I'm just gonna denote it as capital I, and that's given by the worst case is just log m, right? Minus this guy, which is just plus summation from I, okay, over I pi log base 2 of pi. And so that's this term, this is the information content of this message. So the higher this thing is, the less compressed can this thing become. So something with very low information, and yeah, so something with like very low information would just give us something that's really, really compressed, essentially, right? Now, so wait a second, something is messed up. Something with really low information will give us something like that. Oh, sorry, no, something with very low information will actually give us sort of very bad compression, right? Because, yeah, I mean, think about it. Information content, right? Okay, yeah, right, okay, that's actually the thing. So something with big information, that implies that it's like really compressed, because the difference of the entropy from the maximum value to whatever it is right now, it's big enough. So then we can say that this is going to be like really, really compressed. So big information implies very compressed, and low information, that implies not so compressed. So it's sort of comparable size. Right. And yeah, so this thing can also be termed as information gain in a way. How do I even say this thing? But again, not exactly. Yeah. Anyway, so information gain is actually a slightly different thing, but this is the information content, and we'll be using something similar to that soon enough. So this is the entropy. This is something that characterizes how impure your data is. As in, something that's very pure would have like only one character throughout, but something that is sort of impure will have a mix of characters with equal probability. So as in, you cannot actually sort of predict what's going to happen. So something with a low entropy, that gives us purity. And another way to say this is like predictability. Something with a high entropy gives us impurity. Cool. So with this terminology, we have the second metric for, so the first metric for classification. So I'm just gonna delete that. Actually, before that, we should probably deal with another thing. So that another thing is called information gain, which is actually based on this thing. So like what we essentially do is that suppose you had your, how do I say this thing though? Mm, right, I guess. Yeah, this is sort of complicated. How am I gonna say this? Okay, let's think of it like this. Suppose you had the once again the same example. You have a big text file and it's like doing stuff, whatever. And you have like different characters over here. We don't know about that, and it just so happens that this whole thing contains a lot of characters which are like really similar, but this thing contains characters which are quite different, right? So if we sort of partition this text file at this particular point, as in convert this to make two text files, and then we compress both of these text files. So this is compressed into a smaller section, this is compressed into a bigger section. This is like compressed slightly longer. Then the net effect would be better than if we just compressed it like straight up without caring about the partitioning. And so the gain in the compression is something that you can sort of say is the information gain. It's not exactly the definition, no, this isn't very much the way it should be, but it's analogous to that, as in what gain did you get by splitting your data in a way such that one of the parts is, or maybe both of the parts are now easier to compress or predict. So whenever I say compress in this in this example, this is sort of equivalent to prediction for a classification model. And so here what I'm doing is basically something called a decision tree thing, but like let's not get too deep into that. So what we need to do is just figure out what's the gain, right? So the entropy over here, that's given as just whatever was the entropy initially, it was summation of pi natural log of pi. So whatever the thing was, that's entropy initial. Now the entropy of the first text file that we have created, that's going to be summation of pi1 natural log of pi1. So once again, these are like the probabilities in this text file only, and entropy of the second text file is summation of pi2 natural log of pi2, right? So yeah, it's negative of that, negative of that, negative of that. So these are, I shouldn't say natural log, but I've got used to this, so I'm just gonna say log. Okay, so right, so these are like your entropies, but now the thing is that the size of the split, those might be unequal, and also the fact that this is actually a bigger data set. So what we should essentially be calculating is the weighted difference in the entropies, as in initially your entropy was this big, but now you can't just say that, oh, it's now this plus that. No, that's not correct, because the size of this also matters, right? So like now what's the expected, so okay, let's actually go with this thing. What's the number of bits required to compress this thing? Well, it's going to be n, so n characters in this initial text file. So n times this s naught thing, okay, that's the length of the first case, minus what are the number of bits required to express in these two compressed files. So in this case it's just n1, so maybe you split it such that this whole thing is now having n1 characters. So n1 that times of s1, and then this would just be n2 s2, right? For the second file you just require these many bits. And so the reduction in the number of bits, that is so once again you can write this whole n thing as like what was I actually going to say? Yeah, so you can just divide by this whole n thing and then say the expected number of bits required, like for this whole text file to be compressed. The difference in that expectation, that would just be s naught minus, so what's n1 upon n? Actually we shouldn't give it a name right now, but yeah, this is the reduction, and this thing is called the gain or the information gain. I'm just gonna call it as g, pretty much, like, yeah. So this is the gain information upon splitting um, at a particular point, and this is like very much analogous to uh, you know something that we do in decision trees, as in um, we split a more I shouldn't say more we split an impure sort of impure data set into two data sets, in which at least one of them is more pure than the initial one. So in that way we can say that okay, we are making gain. Yeah, so this is called information gain, and that's like, what do I say, that's like a metric that we used for classification. So how do I actually say this thing? So it's like particularly useful for decision trees, as in I don't know how to relate this to models in general. Because in general, what something that we actually do use is something called cross entropy, which I don't want to be getting into right now. But yes, this is actually a metric for classification. Just trying to figure out how am I gonna present this. But anyway, you'll get an understanding of this once we go for decision trees. So that's classification matrix. We just use information gain. So entropy is obviously something that you can use. This is probably not a good idea. So we just use information gain. And another way of saying information is like, so without using this entropy thing, is also to use this thing called the Gini index. So entropy is given as this formula, right? And entropy is just negative summation of pi natural log of pi. Sorry, log of pi. No, there's a natural log. The Gini index, which I'm just gonna call as G, is given as 1 minus, I think minus, what's the thing? Yeah, I think so. 1 minus summation of pi square. So something which is like really pure would just have pi equal to 1 for one particular I, and then the Gini index would be 0. Something that is like really impure would have equal probabilities, and so since it's square of that, so it's like 1 upon the number of categories that you have. Right, so that would be a really impure data set, something like that. So you use these two to calculate the gain in information, and that's actually the thing that you use to figure out, okay, how good did our classifier do. So that's the model. So information gain, using, so one, you just use the entropy, which is negative summation of pi natural log of pi. So log of pi. Why do I keep doing this? And second is the Gini index. I'm just gonna call it G. I don't actually know what I should call it this. So it's just 1 minus summation of pi squared. Okay, but once again, this is something that is particularly for decision trees. We want to have something that is slightly better, right? That's also more interpretable. So finally, we are going to go to something that is better, in like more interpretable, and that's called accuracy. Yeah, I know this is like really, how do I say this, anticlimactic, but whatever. And accuracy is actually sort of what we want to maximize, right, in the end, at the end of the day. So this is like very easy to calculate. For each data point, you just figure out what's the predicted category, and if it's matching with your actual category, you increment the number of correct predictions by 1, and then you divide by the total number of predictions, and that's your accuracy. So I'm just going to write it as like accuracy, not really dealing with anything. And so another classification, or actually there are 3 more classification metrics, whatever. So these two are called precision and recall. And the last one is called F1 score, which is basically like just the SHM. So F1 score, this is just the SHM of the precision and recall. just precision and recall. And these are metrics for a particular category. So you're doing classification, right? And let's just say that you have categories. So I'm just gonna delete all of this actually. So let's just say you have category A, B, C, right? Then for category A, you want to figure out what's the precision, as in from all the predictions that you have made, how precise you were. So that's given by this thing, that your y, the y hat is the predicted value. That should be correct. As in it should be equal to y, but also this is only for this particular class. So A, upon the number of predictions in which you did predict A. So just y hat equal to A. So that's like how precise you were. And then the recall thing is how much were you able to recall. So this is the whole data set in which you had the target to be A. So what fraction of that are you able to recall upon predicting? That's this thing. So that's these are like your metrics for classification, right? This is also sort of written using the confusion matrix sometimes. So okay, so confusion matrix is something like this. So these are like your predictions, and this is the real truth basically. So for a particular class, you either predicted it's that class or you did not, right? So is A and is not A, and over here as well, that it is A and it's not A. So in case you predicted that okay it is A, then you're saying that like we are positive that it is A, and if that's true, we just say it's a true positive. If it's false, we say it's a false positive, right? So as in like false alarm, so false positive, something like that. And over here you just have a true negative, and so this should be the thing. This is a true negative and this is a false negative, as in you predicted a negative but then it falsely predicted, so it's false negative, something like that. So that's the confusion matrix. Let me just check this up real quick. Right, so the metrics for classification, those are, so okay, this is for the binary confusion matrix. Right, yeah, this is actually the thing. Cool. So this is called the confusion matrix, and so precision recall can also be written as, so this is the obviously the precision, this is the recall. So this can be written as the true positive upon, so y hat equal to A, as in you predicted A, so it's just all the positives combined. And this, so I'm just gonna say this is actually true positive plus false positive. Now this recall thing is just a true positive upon all the cases when the prediction does not actually matter. It's like the real case is A, so that's just the sum of this thing, and so that's just true positive plus false negative. Cool. And so that's your precision recall. So precision is just this quantity, that y equal to y hat equal to A upon y hat equal to A, and the recall is just this quantity, that y equal to y hat equal to A upon y equal to A. Alright, F1 score is the, sorry, why am I writing as SHM? It should be harmonic, just HM. Yeah, cool. Let's delete all of this. Okay, so that's the F1 score. Now there's this final thing called the Matthews coefficient. So I'm just gonna write it as Matkoff. Yeah, and that's given by this thing. Wait. So it's given as true positive times true negative minus false positive times false negative. So once again, the coefficient matrix is something like this, that this is predicted. So maybe let's just say y hat equal to a, y hat not equal to a, and this is like y equal to a and y is not equal to a. And so this thing is a true positive, this thing is a false positive, this thing is true, sorry, false negative, this thing is true negative. Cool. So now the Matthews coefficient thing is just given as the determinant of this matrix. So just this times of that minus this times of that upon the geometric mean of these quantities, right? So the sum of these basically. So essentially what you want is, let's just say confusion matrix is given, so the confusion matrix is given as C, which is the determinant of C upon the square root of y equal to a, y not equal to a, yeah, and then the square, sorry, and then this stuff, so y hat equal to a and y hat is not equal to a, and that's your, what do we call this thing, this is your Matthews coefficient, right? Cool. So just like multiply all of these sums and then you take a square root of that, and in the top you have the discriminant, sorry, determinant, what am I saying, right? So that's the Matthews coefficient, just the determinant of the coefficient matrix upon square root of y equal to a, y hat equal to a, and then y not equal to a, y hat not equal to a. And yeah, that's like all the matrix for classification and regression. So now we can finally move to like the first real model that this is actually not called the F1, so it's just called the F score, sorry for that, right? So now we can finally move to our first real model and not care about all of this like stuff right? And so let's go for this thing that we call decision trees. Okay, also I think I kind of forgot to mention this negative log of pi is the self information. I think I did mention that, whatever. So we are going to the decision tree algorithm, which is called ID3. It's a greedy algorithm. So once again, what's a decision tree in the first place? So suppose you are given this sort of a table, you want to predict y, which is it's like we're doing classification, so it's a binary output, it's a 0 or 1, and then you're given some values which are also like just discrete. So maybe you're given like maybe something like this, that is it going to rain today? Not that exactly. Maybe like I don't know, what should I say, will I get a holiday? So is it holiday? And maybe you have something like, is there rain today? Is there maybe maybe there's like workload today, right? So if there's workload today, then you might just say, is it holiday tomorrow or something? So holiday tomorrow. Cool. So if it's like raining tomorrow, that might happen. If it's there's like quite a bit of workload today, might happen. Or maybe there's like some sickness going on, so like that would give us a holiday, who knows. I don't know, I'm just making up a random example. So let's just say all of these are like binary cases, so it is there or it is not there. So maybe we have like 0 0 0, then this is like, no, you don't get a holiday. Maybe like have 1 0 0, okay, you still don't get a holiday. Maybe like you get 0 1 0, you still don't get a holiday. But maybe like you have two things, then you get a holiday. And maybe this isn't actually all that important, and then you still get a holiday, and so on. So you're given a big data like that, right? So you're not predict this, whether or not you're going to get a holiday tomorrow, right? How do we do that? Well, So the most interpretable way of doing this is to deciding whether or not, so deciding using these features directly. So like, okay, the decision goes like this. So is everyone sick today? So if that happens, then maybe like, yeah, so you do get a holiday. And if no one's sick, then there's still a possibility that, okay, it could be that it's raining or something like that. So maybe like you have the condition that it should be raining at the same time there should be workload. Only then can you get a holiday. So in that case, if it's raining, then there's two conditions. So if it's this is a 1, this is a 0, by the way. So if it's raining, then you have this another decision that you want to make, that is there quite a bit of workload today. So if it's not raining, then let's just say that, okay, you don't get a holiday directly. But if it's raining and you have a workload, then you get a holiday, otherwise you don't. So maybe that's one of the, this is like a decision tree basically. And so how do we build trees like that? That's what the ID3 algorithm does. So the whole idea is that let's just forget that there was anything before it, and we just wanted to figure out what is the first decision that we should be making, right? So you just want to make one decision such that you can predict the best. So how do you figure out what best means here, right? Like, what do we mean by the best? In this particular case, what we are saying is that we want to minimize the entropy, the net entropy of our prediction, right? So if you like had to express all of this stuff in a file, then the expected number of characters required, so expected number of bits required for each character, that's pretty much the thing, right? So you want to minimize that entropy. Yeah, that's the thing. Now how do we do that? So maybe it could be like so in this particular case, as you can see, that wherever you have a 0 for the sad face, it's already 0. So if it's 0, then all of these are just having 0 0 0 everywhere, like in the targets, right? So then the entropy is already 0. So this is an s equal to 0 case. And then once you do a 1, this is already an s equal to 0 case. So you actually kind of don't want to be classifying further. I'm making more decisions. And so in that case, you're already done, right? So the way that we figure out what to split on, right, what decision should we make, is that we figure out the feature which gives us the best split, which is the best information gain, right? Remember what information gain was. It was just a reduction in the entropy, which is the reduction in the expected number of bits required, right, for each character or for each class in this case. And so that's what the ID3 algorithm does, that it just figures out the best feature, it splits on that, and then, well, if entropy is 0, good job. If it's not, keep splitting, right? And there are conditions like, okay, maybe you have reached the maximum depth, then you have to necessarily stop or something like that. So given infinite time and resources, and you would certainly be able to make so many decisions such that like every single case is covered, and then you're pretty much done. And that happens when you do have a relation correctly. There's a possibility that, okay, maybe you actually cannot figure out what this thing is, like there's no way to predict directly. So like, I don't know, maybe this feature was somehow missing, right? You didn't actually record that, and so now it's complicated, right? Like it could be raining or it could not be raining, and you would still say that's not kind of complicated. How do I say this thing? Yeah, right. Okay, let's consider these two cases. Let's consider these two events, that it was not raining in both cases, and it was having, and there was some workload, but in both cases you didn't get the same result. Like in one case you got a holiday tomorrow, but in one case you did not. And so in these cases, even if you give it infinite time, it can't just like keep splitting, because it doesn't make sense in that way. Yeah, right. And so you would eventually just get the best information gain, but you do not get zero so like you don't get zero final entropy. That does not happen. Right, so that's the decision tree algorithm, so ID3 algorithm. And yeah, it is actually pretty simple, isn't it? Now obviously putting this in code is kind of hard, but let's forget about all of that, because what matters is that we understand what's going on. And so this is like decision tree. Cool, pretty simple, right? Okay, so once again, to summarize, in decision trees what we do is find best feature to split according to, as in like maximize the gain, maximize information gain for that particular split, right? So info gain. All right, and yeah, just like that's actually the whole thing. That's all we need to do for this algorithm, and just keep doing this. That's pretty much it. Obviously you cannot split if your information gain is negative, but actually that doesn't quite make sense, right? Yeah, but anyway, let's go to the next thing. So we have the ID3 algorithm for decision trees. Right, what was I going to say though? Yeah, so that's decision trees. Let's go to the next model. Actually, there's one thing that I sort of didn't mention, that is when you have real sorry, I shouldn't say real, when you have continuous outputs and continuous inputs. So this is just for classification, but decision trees can also be used for regression. The way it happens is that you make decisions based on your features again, but in each case, instead of returning a 1 or a 0 or a class, it could be a multi-class thing, not just a binary. What you return is a value. So you return like y1, y2, so on. And so these values are just the mean values of the part of the data set that has this, sort of condition on these features, right? Maybe this was like feature 1 should be 1, feature 2 should be 0, something like that. You have these conditions, and then whatever data set is following that condition, you just figure out the mean target value and then return that. In that case, in the previous case for classification, you just figure out the mode target value and we return that. In this case it's the mean, right? Makes sense, obviously. Okay, now what happens if your features, if your attributes are somehow continuous, as in they're not like 5 different classes or binary or something like that. There are things like 0.1, 0.2, 2.3, whatever. These are the values. In that case, what you do is that the decision you make is based on whether or not the value is bigger than some particular set value. So maybe like x1 bigger than 2, something like that. So how do you figure out this value, by the way? Yeah, that's actually a really problematic way. So it's a really problematic situation. What you have to do is that you just say x1 is bigger than some number a, but you figure out every single number a could be, and then find the best one, right? The one that maximizes the information gain again. So now this is, yeah, so you are maximizing information gain in 2 things. One is which feature you are going to split on, and the other is which value you're going to use to split. But yeah, enough talking about that. It's just a recap. We're not gonna go too much into the details. Okay, so that's decision tree. Let's go to the next thing. So what are like the good points and bad points about decision trees, right? So once again, just to recap, for the decision trees, we first did the ID3 algorithm, right? I think by now you have a good understanding of that, right? It uses information gain. Okay, this is actually probably not a good idea to be saying this, because in case of regression it could be using the MSE, which is something it should be using, but in case of classification it does use just the umbrella term that we're calling information gain, and information in most cases is just the entropy, or more like the difference of entropy. But yeah, Okay. Okay, cool. So what are we going to do? This is just gain basically, like whatever metric you're using to figure to like say how good or bad your classification is or regression is, the gain in that metric, if it's actually a positive, uh, if it like being bigger means better classification or regression, in that case fine. Okay, so maximize gain at every split. That's sort of the whole idea of the ID3 algorithm. Cool. Now, so that's like what decision trees essentially is. Trees, not trees. What essentially it does. Let's figure out its pros and cons. So one very big pro is that it's interpretable. As in, we can understand what's going on, right? We're not thinking of it as a black box that just does what it does, and we don't know what's going on behind the box that we've put it in. So that's like sort of the only pro that it has. It's a strong learner. In machine learning, a strong learner is something that easily overfits. That's a con, basically. Easily overfits. Now, decision trees are like pretty versatile. I mean, they can do both classification and regression tasks. So it's one pro, but let's not actually take that too seriously. Okay. So easily overfits, or you can say it's a strong learner. Cool. Now, so that's like one pro, one con. Now the biggest con with decision trees is that they're not powerful. Not very powerful. And when I say powerful, I mean like you will have to train it for quite a bit of time, and you will have to spend a lot of resources on this, and in the end it may still not give you what you desire. And once trained, you can't train it again, so you'll have to train it again, like a whole new decision tree, which is problematic, right? So that's a problem. Now another problem is that learning the best decision tree is hard. So essentially we're not even solving the problem. We're once again just stuck in that whole local minima case, which happens by the way everywhere. It even happens in neural networks and anything that does continuous optimization with a non-convex function, right? But yeah, it does suffer from local minima pretty much. So yeah, so learning the optimal tree is hard. Best we can do is greedy. Compared to something like linear regression, this is a bad sort of scenario, right? We don't have an analytical solution for some reason. So yeah, these are all the pros and cons of decision trees. But yes, interpretability is a very big pro, because like say you want to tell someone that you are like using a model to predict stuff, and you give them a neural network and all the weights and biases, and they can't make heads or tails out of what's going on, like what is the model actually doing, then they won't really trust the thing, would they? But instead, if you give them this decision tree thing, like which has a good graphical representation, it's very interpretable, you can certainly understand what's going on, then they'll be able to follow along and make sense of it. So that's a big pro. Okay, let's go to the next thing, bias and variance. Okay, so that's just like one of the first models that was taught to us in this course. Now let's go to some more terminology with machine learning. Yes, this whole course is just that essentially. It's just a lot of terminology and in between some useful bits. But let's get to this terminology first. So bias and variance. And yeah, these are not mathematical terms till now at least. So variance is basically like another way of saying you know, of like being too delicate, as in like being too too much of an overthinker, as in you stimulate it a little bit and it changes direction completely, so it varies a lot, right? So this is usually this happens with overfitting, right? So this is analogous of saying overfit, and bias is analogous to say underfit, right? So whenever you say something is high bias, it basically means that the model is underfitting. So maybe like you are like training a neural network, and then you want to figure out how is the accuracy on the test data set changing. So you're obviously training on a training data set, and it's gonna go with like higher and higher accuracy. So this is the training data set, but on the test data set maybe your accuracy isn't doing so good, so it's like, oh sorry, yeah, this is a bad graph. So on the test data set maybe it's something like that, right? So this is the number of epochs that you have. So in this case what's happening is that initially it was underfitting, obviously, because the model isn't really, it's just like having random weights, so it's not actually predicting anything at all. At one point it was doing pretty good, right? But after that it overfits the training data set, and it does not like fit well with the test data set, and so yeah, it causes some problems essentially. And so that's yeah, this is called a high variance thing. So in case of decision trees it's even more explicit, as in you just have the depth of the decision tree, the maximum depth, you set it initially, right, before training the data, before building a decision tree. So let's just say that you build a decision trees based on higher and higher max depths. Then as your depth like gets really really big, what essentially happens is that the decision tree just overfits on our training data set, right? It just gives you the maximum information gain that you can get, but that does not generalize well. Like we can't use that model to predict on the test data set because we have gone a bit too deep like into the training data set, right? Where we have started to overthink and assume patterns which are actually not there, and so that causes the accuracy on test data set to fall, right? Yeah, so this whole part is called high bias, right? So in case of decision trees it's easy to see why it's called high bias, because you're just making one or two decisions, so you're completely biased over some particular feature, right? You're not thinking much. But this is called a high variance case, as in you can't make a good decision because you're thinking too much, right? And decision trees are very much like how we make decisions, pretty obvious, and so these are like understandable terms in this context. So once again, variance is overfitting, bias is underfitting. That's all you need to know. Like everything else is just people trying to make sense of stuff. But these are like the only two things that you use these terms for: overfitting, underfitting. That's it. Next. Okay. Cool. So once again, something that is characteristic of strong learners is that they overfit, right? As in they have high variance. Then so given a train data set and a test data set, they will be easily able to overfit on the train data set, and then may or may not do so good on the test data set, right? But essentially what we have done is like we just provided one snapshot of the real world to the decision tree, so it might have just assumed stuff and like it is living under a rock basically, and that's why it did bad. So if we give it more and more data, it will obviously do good. But another way is to train multiple decision trees and then say that okay, this one is living under rock 1, this one is living under rock 2, and so on. And so you just have all these decision trees, you treat them like people, you make a council out of them, and then you let each tree vote, and then that's how a decision is made, right? So yeah, we're like building a whole government for using decision trees at this point. But right, that's this is what is done in ensemble, I don't know how to pronounce that, ensemble learning, as in you train multiple different decision trees and then you use the use the predictions from each of these guys to sort of make the in just like the mode prediction in case of classification, or the mean in case of regression. Like someone says, oh, it looks like maybe it's like its cost will be 3,000, someone says its cost will be like 2,000, someone says it's like maybe like 2,500, and then you like take the mean of them and say, okay, it probably is 2,500 if everyone's like somewhere around that. Yeah, so it's like very interpretable. It makes sense why we would be doing that, because that's just how we do it in real life as well. Like in real life, you have people who make decisions. So people are analogous to decision trees basically. And you have many people, and then combine each of them, and what you get is like one government, and that is like something that makes good decisions basically, right? Like each of these are not necessarily going to make good decisions, but when you take advice from each of these strong learners, as in people who can easily assume stuff, easily overfit, easily say that, oh, that's just the way it is, and are sort of stupid, but but you combine all of these people's opinions, you get amazingly good results. Like yeah, you can run countries with that. So that's what we do in machine learning as well. Like we take a lot of people, when I say people, I mean decision trees, who can assume stuff easily, and then we combine them to get an ensemble, right? Now before this, we probably should be going into this cross validation and all of that stuff. Let's just start. Okay. But okay, even before that, yeah, I probably should encourage why we are doing this. So notice that depending on what train data set we give the tree, it will have different structure, right? Yeah, it will be living under a different variation of the rock. So what we can do is we can train the same model. So like we can train decision trees for many different variations of this train data set, right? And then choose the one which has the sort of let's not say choose the one, and okay, let's just say like combine the accuracy of each of these, right? Okay, how do I even say this thing? This is a complicated scenario, isn't it? Okay, so if this is something that's actually not just limited to decision trees but in general, so let's just say that you want to figure out how good, so you have come up with a model of prediction which you have not tested in comparison to other models yet, and you want to figure out, okay, how good does your model actually predict, right? So you can't just be training on one data set and then predicting on one test data set and say, oh, we are done, like this model did pretty good, because it could be that in real life the data set that you will get is completely different, and it could be that in the training you just got lucky. And so what you should be doing is something that's called cross validation, as in you train on so this is like a test data set, this is also a test data set, so this is the whole data set, and you train on the remaining part, the part that is not used for test, and then you predict on the test data set, right? And every time you get some accuracy, right? So this gives you like maybe an accuracy of, I don't know, 99%. This was like really good, you just got really lucky. This was giving you accuracy of 80%, or maybe this, sorry, not degrees, what have I been writing? This may be giving you like 95%, so on. And then you combine each of these results, take the mean of that, and then you get some accuracy, maybe like, I don't know, maybe like 90% or something, right? And then you say, okay, on average our model does this good. You cannot just say that our model predicts with 99% accuracy, because that's just for one particular case. You should be doing this many times and then say, okay, our model does this good, right? That's a better sort of metric, right? The average accuracy over the whole data set, right? So in real life, whenever you will get a data set which will actually be much bigger than whatever you got, because you will have to be making like real-time predictions or something, like, I don't know, that will be so this whole thing is just a subset of everything that you could possibly encounter, right? So yeah, so taking another subset out of that and then training on that, that's not good. What we should be doing is taking many subsets, many variations of the same thing and then training on that. And so then you can say that, oh, on the whole data set, the test accuracy is 90%, right? Yeah. And this will be a good measure of the accuracy that you would be getting on the real life data set. This is called cross validation. Okay, cool. This is ensemble learning. Okay, let's not have this stuff. So this is the whole idea. Decision trees analogous to people, ensemble analogous to government. Okay, cool. So far we have done cross validation. Now let's go to something that's called okay, so where were you once again? Yeah, we want to predict. So we wanted to compare our model to the other models that are there, right? So once again, one way is to just be using whatever other model you want to compare it with, and then figuring out this accuracy. But another thing is that maybe both of these models are actually like working good on our data set, and that's not because the models are good, but because the data set is poor, as in it's like easily predictable. In that case, what you should be doing is you should be training a dummy model, right? So train a dummy so that you can see whether or not the effect, like high accuracy, is because of the model, or maybe it's because the data set itself is just really stupid, as in like it doesn't actually have all that much need for model to learn anything. Like even a child could predict based on that data set, something like that, right? Yeah, so that's called a dummy model. So let's say you are training some sophisticated model, and it's like on particular data set with respect to the how do I say this thing? Okay, let's just say you're doing some sort of a what do I say? Okay, a dummy model, right? Okay, so usually the dummy model is just like giving us the mean of the targets or the mode. I can't really draw a picture for that. But let's just say that your real data set is given like sophisticated model that's giving you an accuracy of 99%, like just 95%, and your dummy model, naive basically, that's giving you an accuracy of 93%, then you should probably be concerned, because what that means is that the data set is like really poor. So yeah, then that implies bad scenario. Then that implies that the data set is easy, right? So yeah, just be aware that high accuracy does not mean better model. Okay, so far we have done this dummy classifier thing. Let's go to the next thing. So the train validation tests split. So far you have seen the train test split, right? Like we get the data set and we split it into a train and a test. And the reason we do that is because you don't want to be predicting on parts of the train data set again, because it's like being given hundreds of mock tests and then memorizing all of the questions in the mock test, and just answering the questions based on the mock test. That's not how it should be. The thing is, you should be given 100 of mock tests, and then you should be asked to solve questions similar but not exactly same to the tests, right, in the real exam. So that's why the train test split is there, as in you train on lots of questions which will never be repeated, and then you test yourself on questions which are new, right? Yeah. uh, so that's good and all, but now here's the thing. So let's just say that some guy is preparing for some really hard exam and he has, I don't know, maybe three strategies. Maybe the exam is like made of three subjects and he's really good at one subject and he thinks that okay, maybe choosing the other one to do first would be easier because then you'll get lots of time to do the one that you are good in or something like that. And so he has maybe like three different strategies and he wants to figure out what is the best strategy. How would he be doing that, right? So you obviously cannot do it like, okay, so we'll just say with strategy 1 we train on a data set and then we look at the accuracy and maybe it was like 90%, and then with second accuracy, so this is like strategy 1 you get this accuracy, and then with strategy 2 you might have got 99% accuracy, and maybe in strategy 3 you might have got 98% accuracy, right? And then you say okay, 2 is the best one, so let's just go with that in the real exam as well, and then he fails. Why did that happen? Because it could be, it certainly is possible, that yeah, what was I actually gonna do? I was actually gonna do something, right? Yeah, right. Okay, so the best strategy for this particular training data set, that's obviously 2. Maybe it's because like this data set contained a lot more memorization based questions and less of a learning based questions or something like that, and so he just went with rote learning, and that's what strategy 2 was, and so he succeeded. But in the actual exam it wasn't the case, and so he didn't succeed. Could be a thing. So then what should we be doing, right? Yeah, that's a very much valid question. So what we should be doing is, so we know that all of these questions are a good representation of what's going to happen in real life. So what we can do is just, so one way is obviously to like have both of these comparable, as in like training it on as diverse of a data set as you can. Like that naturally solves the whole thing. But if that's impossible to do, then the usual way of doing it is to train on a subset of the actual training data set, and then figure out what the best strategy is on a validation data set, as in, because once again we run into the same problem that whenever you want to figure out what is the best strategy, you don't want to figure out on questions that you already have used to train yourself, right? It runs with the same problem, like you memorize, you by this point got used to those kind of questions, and so it doesn't make sense for you to be testing yourself on the same thing again and again. So you should be testing on something that is new. So that's particularly a validation data set, as in you are validating whatever you learned, right? So you have learned how to deal with these questions using 3 different strategies, and now you test all of these 3 different strategies on the validation data set. So this is the train, this thing is the validation data set, and this is the test data set, right? And now on this case you get maybe 1 has a 99% accuracy, and 2, okay, which is 90%, and 2 has an 80% accuracy, and 3 has a 70% accuracy. In that case you'll say okay, 1 is the best strategy, and then you do it on the test data set and you actually get a good sort of accuracy, right? That's the way it should be. Yeah, so what was I going to say? So this always has to be done, like you do it on the validation data set first to tune your hyperparameter. Yes, these strategies are actually like hyperparameters. So but it's not necessarily just like a hyperparameter that you want to be tuning. You could be choosing different models or different variations of the same model or something like that. So in our case we would be tuning the hyperparameter that is called the depth of our decision tree, right? You like gauge what the questions are like, and then figure out okay, what's the limit to which you need to think, as in the bigger the depth is, the more the model is overthinking, right? So which depth till you should actually think. Maybe the questions are just supposed to be really simple and you're overthinking, and that gives you like wrong answers all the time. So that's something you do on the validation data set, right? And this whole thing is once again sort of a part of training, and that gives you the best strategy, and with that strategy you tackle the real life problems, and a representation of a real life problem would be the test data set, which is completely unseen. But once again, we run into the same problem that maybe this strategy one was good because you chose the train and validation data set in this particular fashion, right? Like, what if you chose a slightly different train data set and a different validation data set, and things would be sort of different, right? So we have to do a cross validation inside of this as well. Like inside of, so forget about the test data set for now. You only have the train data set, and you have split it into actual data set and the validation data set. Now what you'll be doing is you'll be having different so this is like a validation thing. You'll be having different snapshots of the train dataset which you will train on. The remaining you use for validation. And let's say you do it like this: for strategy 1, what's the mean accuracy? And maybe that thing is actually really poor, 80%. And for strategy 2, maybe the accuracy is even worse, 70%. And finally for strategy 3, it's 90% accuracy on average. And so obviously you should be going with strategy 3 because on average it gives you a better accuracy, right? And then when you test it on the test data set, you probably will get a better accuracy, right? Yeah. So once again, this thing is called nested cross validation, and here we are essentially doing hyperparameter tuning. So we are finding the mean value of the metric for different strategies, right? And what I should be saying is different hyperparameters, right? And then with these values of the mean values of these metrics, you figure out the best hyperparameter and you use that on the test data set. Cool. And once again, this has to be like, this outer fold thing also has to be done a lot of times. Maybe maybe this train data set was just something that you got lucky on, and so you have to be having different test data sets and different train data sets, and inside of that different train and like actual train and validation data sets. And so yeah, it's a nested k-fold. Yeah, I kind of skipped over that term, right? This cross validation thing is actually like k-fold cross validation. All right, cool. So what we have done now is nested k-fold for hyperparameter tuning. Right, so the whole idea is you have the whole data set, you partition that into test and something which will actually partition later, but then with this thing you actually like partition into different train and validation data sets, right? So maybe like these are the hyperparameter values. So this is like maybe the value a1, or let's say h1 value for the hyperparameter h. This is h2 and h3 and so on, whatever. And then you get different values of the accuracy or whatever metric you're using. Right, and this is maybe a different data set. Right, so you get like these different values, 80%, 90%, 60%, whatever. So you do a lot of times, and then finally you get the mean values. So that's how you actually like figure out the best hyperparameter value. And so maybe you got something like, I don't know, 90% over here, 80% over here, and 95% over here. And so you obviously gonna go with this one, and so that's h3, right? So I'm just gonna do this whole thing over here. All right, cool. So you do that, and then you just do this for many different sort of scenarios, right? and that actually gives you how good is model, right? In our analogy it would be like how good of a learner the kid is, but well, whatever. Next. So that's the train validation test split. Then we have this thing called um, so I think we already like did the ensemble learning, right? Yeah, and it's like a very straightforward thing, pretty easy actually. Now we are going to be doing something that's like used in ensemble learning, and it's called bagging. So the whole idea is that, okay, you want to be, training these strong learners for different variations of your real life data set, right? um, but but you want it to be such that like the variations are not actually too far off, as in they do represent the real life. Like the the more diverse data points you can give to each model, the better it is, obviously, right? And so instead of just splitting your data set into like some parts and then training each model on that, what you could be doing is, so this is like what is done normally. This is like just some normal stuff. Now with bagging, what you will be doing is something like you have this, so this is like just split that. With bagging, what you do is each data set, smaller data set that you create, is done by um, something like this. It's done by having this one point over here and be this one point over there and so on. Yeah, and dot dot dot, obviously. And so you train your decision tree on that, and this is obviously like dot dot dot, and then this thing is your new ensemble, right? So what's the benefit of doing this? I mean, this just looks really simple, right? So notice that here we are sampling the big data set, right? Sampling from the big data set to create a new data set, and we're doing it with replacement, as in it could be that you have this third one being taken from the same data point again, right? And so what that does is like it gives you a more real life sort of feel and so these learners will learn on something that is in fact like how it should be in real life, um, and that will certainly solve the whole problem of the learners being like they're like assuming stuff which isn't there, and assuming patterns which do not exist, because these are strong learners, by the way, right? Yeah, in that way, it's essentially like saying if your government had really, you know if you had like diverse people, it's obviously true that you would be getting a better estimate of the like the common public opinion. um, but if the people themselves are like, well, they're diverse but they are sort of really just living under rocks, then in that case your government, even though it gets the opinion, it's not very efficient, as in like what should I say, as in there is no convergence. You can't say things with surety, and so that's a bad scenario, right? Like, yeah, you get some opinion but then still everyone's dissatisfied with it. Like, yeah, there's justice to everyone's opinion, but and yet at the same time no one actually got their wish fulfilled. So that's something that should not happen. So what we do instead is like we train these strong learners on environments which are actually like the real life scenario, and so these people will really be sort of similar in a way. Yes, these will be diverse, they're stronger, and they do overfit, but even then they are sort of similar. Yeah, and so that's just what bagging is. And I can't go into more depth than that because I frankly do not know enough about it. uh, but I think that's what bagging does, and the reason we do that is to obviously reduce overfitting, right? uh, to reduce the assumptions that these strong but stupid learners make, um, right? Naive kids, sort of. Yeah, decision trees are just like naive kids. So anyway, um, yeah, so what this does is just it reduces the variance, obviously. So bagging and ensemble learning in general just reduces the variance. Okay, now there's some like extra stuff about this bagging thing, which is like if your new datasets are all of the same size as the older datasets, then as your older dataset grows in the size, then approximately 1 minus e power minus 1 times n is the number of unique samples that you have in each of these datasets, which is not that big. So it's not that that bad. It's actually like a good enough number, right? And so we shouldn't be too worried about this. And as a matter of fact, it cannot get it cannot get actually like smaller than that, I think. Wait a second. So the actual thing is like 1 minus 1 upon n to the power of n, right? Yeah, 1 minus of that. So as n approaches infinity, this thing approaches e power minus 1. Sure. Yeah, right. How does this vary? So n equal to 0 is problematic. N equal to 1. What does that give us? N equal to 1 gives us 0 power 1, which is obviously just 0. So it just is 1, right? So it goes from 1 to 1 minus e. So it's decreasing. So what we are essentially saying is that as n changes, so n equal to 1 would have given us a 1 value, and at 0 you would have got something crazy. So not caring about that. It like decreases and eventually it reaches this value 1 minus e power minus 1. This is the minimum. It cannot go beyond that, right? So you will always for sure have more, in fact, than these number of unique samples, obviously. All right, so that's bagging. Let's go to, and this bagging thing is also sometimes called bootstrap aggregation. Yes, a fancy word for something pretty simple. Let's go to the next thing, and it's called boosting. So bagging is when you have like strong learners which assume a lot, and then they don't make, like they're naive as such. Like they live under the rock and they don't know what's going on in the real world. Now boosting is usually done with a weak learner, someone who is very critical of everything, who does not assume a lot, and for that reason he's not very effective as well, right? So this guy only like learns stuff which is like happening a lot as such. It needs like a lot of data to be able to, like, yeah, it recognizes patterns obviously, but it only recognizes them if these patterns are actually like really common. Strong learners are not like that. They are like, you give them small amounts of data and then they'll have like strong opinions suddenly, right? What this guy does is like, okay, it gets a lot of data and then it has some weak opinion even now. And so a weak learner is something that you need to give like lots of hard examples to, so that you know. Okay, wait, I think I'm messing up somewhere. Yeah, okay, right. So a strong learner is something like which actively like makes decisions, whatever. Okay, that's actually funny, but anyway, which actually like makes progress in its thing based on the data that you have given it, right? And once it's done, it's like pretty hard to change that guy's opinion. But a weak learner isn't like that. It's not so hard to change this guy's opinion. So what do? We can give it progressively harder questions and harder events to analyze, so that it has to learn the pattern, right? A weak learner would rather not learn a pattern and would rather not generalize something that he does not know can be generalized. So suppose your data set is something like, you have a few anomalies, and you have most of it's just like something like very much following a pattern, right? And once again some few anomalies, then the weak learner will necessarily, the weak learner will always learn these patterns and never care about these anomalies all that much, right? A strong learner, on the other hand, they will also be learning the pattern, right? But since they overfit, will also like try to learn these anomalies, right? um, yeah, that's what a strong learner does, right? It's gonna overfit easily, right? It assumes a lot of things based on the data that you're given it. A weak learner does not go right into assuming all of that stuff. It doesn't like just jump into it. It's more cautious as such. And so it only learns patterns which are like really visible. And so how do we make a weak learner learn these anomalies in that case? The way we do that is like we increase the weightage to these anomalies, right? So suppose like these anomalies were occurring more frequently, then the weak learner would probably be learning the anomalies as well. And so we do that artificially sort of. So the way we do that is, okay, so you have this data set and you have the learner, and this guy has given you some predictions, and turns out, okay, maybe like there's like two or three some predictions which are just wrong, plain wrong, and the weak learner does not understand what's going on in these cases. And so what we do is that the data points corresponding to these predictions, we boost. So that's actually not the term that we should be using. We emphasize them more, as in we increase their weightage, and then the weak learner must in fact uh, catch on the patterns for these anomalies as well, and that boosts its learning. Because if you did not do that, then it will just keep learning the most visible pattern, and it will not make any progress, right? And so you must in fact give it examples which are counter intuitive, not counterintuitive, which are hard, right? And that way this weak learner, so just a weak learner, that way the weak learner its learning is boosted basically. So the whole idea is like past mistakes are used, so these should be revisited. Right, yeah. And so this is done to reduce the bias, as in the learner isn't just biased towards like what he knows, he has to learn more. So yeah, like it's done so that you don't have underfitting for the weak learner, right? That's what the boosting thing is about. Now this is like a very sort of crude way of putting it. Essentially the way boosting is done is not like this. It's done like this. So you have your data set, right? You split it into parts. Once again, I don't know, you either sample it again, you do something like bagging or whatever. And yeah, it's usually a good idea to be doing bagging, because that way you can deal with high variance. Yeah, and you give this, actually no, you don't probably do this, sorry. Right. Okay, so you have a data set, you train one weak learner on that, and then you get some predictions, and then some of these are wrong, and so using that you give some feedback into the data set. The way this is done is like you have a weight vector. So it's a vector which is giving you the weightage of each question, right? And so you use both of these things actually to train the weak learner. And then once you got the predictions and you see that, oh, some of these are wrong, you use that to give some feedback to the weightage vector. And then once again you train another weak learner, completely fresh, by the way, just a new weak learner, not this guy, because this guy has already got familiar with the familiar pattern that was there, and so it's not of use anymore. Just trash this guy completely. Instead we take a new person who has no idea what's going on, and then we present him this new data set which has more emphasis on the wrongly predicted samples from the first weak learner, and we sort of expect that this guy will do a little better because we're giving more emphasis to the pain points. Yeah, and so this probably gives us like some slightly less number of errors, but then once again with these errors we do this again, and then we just keep doing that. Yeah. And so at this point finally the last weak learner comes in, and who knows, he might actually give us a very like just a clean slate and like 100 accuracy, who knows. But yeah, that's the what whole idea. Now the algorithm that we'll be covering is called the AdaBoost algorithm, and this is done, once again, you reduce the bias, but it's done in a very sophisticated way. Like, you calculate a lot of quantities to do this thing. But anyway, the weight matrix is something that's called W. This will just be capital X, obviously. This will be Y predicted 1, Y2, so on. And this is like your actual, you know, the actual like vector is Y, obviously. Okay. All right, so let's start. So initially what we'll do is that we'll define this weight vector to just be 1 by n. N is the size of the capital X matrix, right? Yeah, so initially just say that, okay, we don't know anything, so we just give equal weightage to everything, right? And so now for each iteration, once we train something, we predict it, we figure out the errors, what we'll do is that we'll change the weights in this fashion. So if you predicted, so okay, yeah, okay, so if you predicted correctly, so if this equation predicted correctly for some certain data point, then we say that Wi is defined as Wi e power minus alpha. And if it predicted wrongly, then we say that Wi is defined as Wi e power plus alpha. So if correct and if wrong, right? Okay, but what is this alpha thing? It's essentially this quantity alpha is half natural log of 1 minus ERR upon ERR, where ERR is the you know weighted accuracy basically, right? So like each of these samples is given some weight, right? So then total weight is just summation of Wi, but the correct samples, or more like the incorrect samples in this case, is like, okay, so it just has summation of Wi which are incorrect, right? And this weighted fraction of incorrect predictions, this is what we are calling ERR, and this is like, yeah, just a number basically, but in a sense it's the accuracy, or more like the 1, or more like 1 minus accuracy, but whatever. So in a sense what we are saying is like alpha is just half natural log of summation of summation over I, and then Wi correct, sorry, incorrect, yeah, I think that's actually correct, upon summation of Wi incorrect. Cool. Now that means like e power alpha, that's just the square root of this whole thing, summation over I of Wi correct over summation of Wi incorrect. Cool. And so we're just saying, okay, just multiply each correct weight with 1 upon this quantity, pretty much, and multiply each wrong, I shouldn't say correct weight, each weight of correctly predicted data point with this with 1 upon this quantity, and each wrongly predicted data point's weight with this quantity directly, right? And so that's something that you use in the training, obviously. Like, you keep doing this, you change the weight, and then you learn a new learner. Wow, that's very weird. But you use a new weak learner, and then you get, once again, some errors and whatever, and then you do the same thing again and again, and you just keep doing that. But now the question is, how do we, since in an ensemble that we are using, how do we give weightage to the predictions made by these guys? I mean, the intuitive thing would be to say, well, okay, this one just gets all the weightage because this is the correct one. But that's wrong. That's not something that you should be doing because you see the fault, right? Like, the hard examples are emphasized again and again. So if you just keep doing that, then this does not actually represent the real data anymore. It represents only the hard part from the real data. Actually, that's not having the hard part. It's like the part which our model feels is hard, or our initial model feels is hard, right? And so we can't just give this guy's accuracy as the final guy, right? That's wrong. And so instead what we should be doing is for predicting on the real world or maybe like the test data set, we would be doing something like this. We'll calculate. So suppose that HM is the prediction by the mth weak learner, right, on the data set that is the test data set. Then what we can do is we can just calculate this quantity. H is the round of summation m hm alpha m, right? So we weight what was I going to say? Yeah, we weight the predictions based on the correct to incorrect ratio, right? So this is the correct to incorrect ratio, and obviously the natural log of that and all that stuff, but you get it, right? It's essentially just that. And so that's how we figure out the final prediction. And so boosting is done to reduce the bias. Obviously it is done to reduce the underfitting because we are like boosting this guy's learning. But yeah, that's pretty much it. So once again, to recap, calculate ERR, which is just summation of WI incorrect upon summation of WI. Calculate alpha, which is just half natural log of 1 minus ERR upon ERR, right? So do this thing. WI is defined as, so WI e power alpha if incorrect, and otherwise it's WI e power negative alpha. This is during the training. And during the testing, what we do is just say that H is the round of HM times, the summation of HM times alpha sub m, right? Cool. And essentially it should be this upon summation of alpha sub m, but yeah, right, I guess this works. Yeah, I guess so. This is a thing, right? Yeah, okay, right. Okay, it should be upon summation of alpha m, because then it would make sense, right? Over here as well, there should be round of that upon summation of alpha m. And so this thing is AdaBoost. Cool. Let's just erase all of that. And this is just boosting. Okay, so far we have done till boosting. Now let's go to the next thing. So we've done AdaBoost, we've done boosting, bagging, train test validation, ensemble learning, dummy regression, dummy classifier. Let's go to random forest, right? Yeah, so a random forest is sort of like bagging. So essentially in bagging, you are bagging the data points, right? In random forest, you're not just bagging the data points, but you're also bagging the features, right? So you're given this data set, the big one, and in normal ensembles, what you do is like, okay, so suppose each row corresponds to one data point in this case, right? Then in normal ensembles, what you'll do is like you create new data sets based on the rows. So this is the first row from this guy, this is like the second row, and so on, right? And that's how you get these data sets. But in random forest, what you do is you do that, obviously. So you take these guys, put them in there, but then you also like shrink this. So I'm just gonna make this slightly bigger. So then you shrink the features by randomly sampling just some features from here, right? So maybe this feature is there, this feature is there, or whatever. And in that way you end up with a way smaller data set, right? So maybe like this guy had 1,000 features or something, and now this just has an 8 or 7 feature thing, and you do it like multiple number of times. So you get a big data set, and then whatever. Yeah, so you do that, and once again you train decision trees on each of this, I'm saying decision trees, but you could like really be just training any sort of strong learner. We shouldn't be caring about that. And then it's the same thing from there on. Like you just yeah. Yeah, right. So it's just like does the thing that you want. So obviously it reduces the variance, right? Because it's ensemble learning in the end. So it reduces the overfitting that happens. Um, but it also like increases diversity. So you remember why we are doing this whole thing, right? Decision trees are like strong learners and they overfit easily. So in this way, what we are essentially doing is making decision trees overfit on different, like completely different features. So like maybe there's like some important feature which is used a lot in your real data set, and all the decision trees use that feature a lot, right? And so what this thing does is that it reduces the importance of that feature, right, and increases the importance of other features. And so in that way, yeah, in that way you're given each feature sort of an equal importance. So the only the yes, so it's not like only the good features are used, and so it increases the variety the of the people sort of the decision trees essentially. So these are like our people in government, right? So it increases the variety of that. Like maybe one of them is an academic, maybe one of them is a military general, or who knows, whatever. So since they have been given completely different features to use, they're gonna give their opinion based on what they know, right? Yeah, not just based on the experience. The experience relates to the data points, but rather than on the way that they have taught to judge, based on the features and what they have made out of it, the decisions obviously. So what are the benefits of this whole thing? Obviously it reduces the variance, because so it reduces the variance obviously, because it's an ensemble learning method in the end. But at the same time it is like computationally better, because you just don't have to be dealing with these many features all the time. And this ensures variety, because the most prominent features are now not always used. So this forces variety, right? Yeah, right. I think there was another point related to this, but I'm sort of forgetting this. Estimator ensures independent models. Oh right, okay, that's the thing. So forces variety, which is the same as saying that your models are completely independent. Ensures independent models. Yeah, so the problem with ensemble learning is that your models can do good, sure, but your ensemble does better than them only in the case that each of the model is actually like independent. As in, suppose how do I say this thing? As in, you have 8 different people, but if 3 of them think the same way, then it doesn't make sense. Like for us to be so okay, if you have 8 different people, but 6 of them think the same way, then it doesn't make sense for us to be actually having an ensemble. It will just be better if we let one person make the decision, right? Because it represents all of that. So we only do ensemble learning when we want to make sure that the different ways that we could think about the problem are all thought about, right? Yeah, and that could or could not happen based on whether or not your ensemble, like whether or not members in the ensemble actually are diverse, right? And so we want to ensure diversity, and that's done by random forest, right? So just as a side note, what we can say is that with ensemble learning, was somewhere over there, right? The ensemble only does as good. so it does better than each member, than its members, only if the members are independent. Yeah, I mean, this is sort of important. So independent or diverse, right? So in this case, for random forest, this is like sort of being enforced, as in they have to be diverse, they have to use different features. It's just not possible that they all think the same way. Okay, so like to just emphasize why an ensemble does this better is, let's just say that you have three different models, and each of them have some probability of messing up. Okay, actually that's another important thing. Okay, so if the members are independent and diverse, at the same time they also have to be having an accuracy above a certain threshold and accurate. The threshold is like 0.5 obviously, but they have to have more than 0.5 accuracy, because otherwise things might go wrong, and I'm going to explain why that's going wrong. Suppose you have three ensembles and three members, and each of them has a probability p of predicting correctly, right? Then for some particular data point you have the probability of two of them messing up as 3 choose 2 p power 2 1 minus p, right? The probability of all three of them messing up is just 3 choose 3 p power 3, right? So that's the probability of your ensemble messing up essentially. So then the probability that your p is the probability of them messing up, right? So that's the probability of your ensemble messing up, right? And so if p is very small, if p, okay, as a matter of fact, if p is like less than 0.5, then this quantity is actually going to be less than 0.5 as well. I mean, okay, much less. This quantity is actually going to be less than if you just did it directly. So it's less than p. Why is that the case? So this thing is just p times of, well, 3 choose 2 is just 3 times of 1 minus p, and that plus p squared. So this times of p actually plus p squared, right? It's basically like p squared times this stuff. So just 3 minus 3p plus p, so that is minus 2p over there, right? So if this thing is less than 0.5, it's like less than 1 by 2, probability of ensemble messing up is this, right? Essentially, I think so. Did I mess up somewhere? Well, that p is gone. It's just p over there, right? 3 just 1. It's only 1 way of doing this. It's 3 minus 3p plus p. That's just 3 minus 2p. Yeah. So, wait. It's like this is p times of 3p minus 2p squared, essentially. Right. And so, okay, this guy is a parabola like this, maybe. I don't know where the y-axis is actually. So this is just a parabola like that, and it has its maximum at p equal to, so minus, right, minus plus, so that's just 3/4 basically, right? So that's when you'll have the thing. So right, at 3/4. So so that means like before 0.5 it's all just an increasing function, right? So we know for sure that whatever is the value at 0.5, before that this guy is completely going to be less than that. So at 0.5, what is this? This is just equal to 3/2 minus 2/4, so it's like 1/2. So that's just 1 essentially. So it's equal to p. That's pretty obvious as well. It's like if it's 0.5, then it doesn't make any difference. Like you just have 10 stupid people, it's the ensemble is still stupid. So if p is less than 0.5, then that implies that this probability is actually less than p, and that's to say like the probability of messing up is for the whole ensemble is actually less than the probability of one of the people messing up. But over here there's an important assumption that we made, and that is that the probability of all three messing up could be written as p cube, or and like only two messing up could be written as p squared times 1 minus p. This is an assumption that we cannot make if the ensembles are independent. So if ensembles are not independent, because then if one of them messes up, it sort of ensures that the other one also messes up because they think in the same way, right? And so we must have them thinking in different ways, and that's what random forest does, right? It makes sure that these are independent. Yeah. Okay, cool. So let's go to the next thing. So that's random forest. Let's go to the feature importance. So yeah, so in decision trees, you know that you based on the features you sort of make predictions, right? Now, how important is a feature? That's like an important question. That's funny. The way this is done is we figure out what's the gain that is because of one particular split. So this is like you had the whole data set and you split it into two parts based on like this particular feature. So let's just say this feature is A over here and A over there. Just two instances for now. Right, in that case you just figure out the gain because of the first split, right? And then the fraction of data points that are seen during that split. So let's just say that the fraction over here is like p sub 1 and over here is like p sub 2, I don't know, p sub 5 or something, I don't know. So 1 2 3, yeah, okay, p sub 5 is cool. So then what you would be doing is, and let's just say the gain is just g1 and the gain is g2. So you'd be doing something like p1 g1 plus p2 g2. That is the importance of this feature small a in this decision tree. Now for multiple decision trees, which is basically what an ensemble is, or maybe like a random forest, the feature importance is just the mean of these sort of just the mean of this quantity in that case. But it won't be like just pg1 plus pg2 everywhere, but so just say this is like the importance of a in tree t1, right? So we'll just do like the expected value of the importance. Okay, this is actually physics notation, I should not be using this. So the expected value of the importance for a tree t of this feature a. So this is an expectation over the different trees that you have, right? And this will be the importance of the feature a in the whole random forest. Easy. So that's feature importance. Let's go to, this is just feature importance. So just importance in general of a. Okay, cool. Next is linear regression, right? So we're finally coming back full circle to the most basic regression model that one could ever have, which is just linear regression. So yeah, the whole point is you are given a target and some data, and you want to say that okay, y is approximately x times of some vector theta, right? So essentially something like yi is just x1i times theta 1 plus x2i theta 2 and so on, right? You just say this thing, and yeah, that's what the idea of linear regression is. So the way we find the best estimate is using the criteria, the mean square error, or you could also use just the sum of square errors, which is what I'll be using, which is just the square of the Euclidean norm of this vector, right? And so this whole thing can be written as y minus x theta transpose times y minus x theta. And so the way we minimize this is obviously using the gradient of this cost function with respect to theta, and we'll just call this thing as L. So we'll just have gradient with respect to theta of L, that's equal to So I usually deal with gradients as row vectors, but whatever, I'm just gonna deal with row vectors. So first we should probably be like expanding this whole thing. So this is just y transpose y minus 2x transpose, sorry, wait, what? Okay, yeah, right. So you just so it's just x theta transpose, okay, 2y transpose x theta, I suppose. Yeah, right. And then plus theta transpose x theta, right? That's what L is. So the gradient of L with respect to theta transpose, yeah, because I usually deal with transposes as the gradient, so in this case we'll just have to take the transpose for it to be the case. That's just going to be, well, this is not dependent on theta in the first place, so just discard that whole thing and just minus 2y transpose x plus 2, yeah, because there are 2 theta terms, so you have to do the product rule thing, so just 2 theta transpose x, and so obviously taking the transpose of that, you just have nabla theta L is just equal to minus 2 x transpose y plus 2 x transpose x theta, right? And so yeah, and so this thing we can set to 0. So for minima, and by the way, this will actually have a global minima because it's a convex function over here in terms of theta, but forget about all that. So yeah, for minima we'll just have nabla theta L equal to 0, right? And yes, it's a convex function, so it will be necessarily a minima and not a maxima. And this implies that, you know, this quantity should be 0, and that's to say that x transpose x theta is equal to x transpose y. Now that implies that theta is just x transpose x inverse x transpose y. This quantity is called the pseudo inverse, right? Yeah, right. So that's just, you know, linear regression essentially. Now this capital X thing, it could be anything. It could be like you're just given some values of the features. Now what you could do is, given some features, you can expand your set of features by, you know, applying some functions on the features given to you, right? So maybe you were like told that, okay, let's just say like y is x square plus 2x plus 1, or more like y is approximately that, right? And yeah, so y is approximately this thing, right? This is the best estimate, and so you're being given the data y and the capital X. Okay, capital X is just, you know, a vector of x1 x2 so on, right? And then you want to figure out the best prediction, so the best model for y, like, and what do you think is like, okay, ax square plus bx plus c, that's probably going to be a good model for y. Now you want to figure out the best values for a, b, c, right? And what you do is that you figure out the x square values for each of these data points, and so what you can say is like, okay, y1 y2 so on, this thing is approximately just x1 square x1 1 x2 square x2 1 and so on, and that times abc. So over here this thing is our theta and this whole thing is our x. So what we have just done is something called polynomial basis, but what we just did is like we took the initial features given to us and then we applied some function on these feature values to get more features, right? And this function necessarily has to be non-linear. If it's a linear function you're applying, that's messed up at multiple levels. So these are called basis functions. So we just like do f1 theta, sorry f1 of x. So if I wanted to write this as a collection of column vectors, then I would write this as f1 theta, not theta, f1 x, f2 x, and so on, right? That's what this matrix essentially is. In this particular case, f1 was the square function, f2 is just identical to the input, and f3 is the constant c function. Actually not the c, the function 1, yeah. And so that's like basis functions. More popular basis functions are polynomial basis, so that's something that we already used. Gaussian basis, so the Gaussian basis is something like that. something like this, that you do fi of x. So this is like one particular function. It's just e power minus 2 sigma square, where your mu I are like equally spaced values on the real line. Maybe this is your 0, I don't know. Your sigma square thing is just something that is a hyperparameter, but like these are your functions that you use to create our capital X. So like given small x vector, then what you would do is like f1 capital X, f2 capital X, and so on. In this particular case, you could like even go for negative infinity or whatever. I think okay, I is an index, so it starts off with 1. So f2 x and f3 x and so on, and that's like a capital X, right? That's a Gaussian basis. So mu I, so it's just mu1 mu2, maybe something like that. So I'm gonna remove this thing, and these are like equally spaced. So these lengths are like identical, in fact. Cool. And this thing is a hyperparameter. And yeah, so that's Gaussian basis. This is a polynomial basis. Another very important basis is called the Fourier basis. So it's like just apply all sorts of sinusoids on your x thing, and then that's how it is. So you just do like fi wow, yeah, so fi x is just sine of omega x, essentially. Yeah. So if it is like just a single variable input, then it's like just omega x, but essentially it should be omega vector and then x vector. So x, I should just say x matrix, or in this particular case it should be something like okay, x omega. Yeah, that's the thing. So omega is just a vector, by the way, right? Next is a matrix in this case. Yeah, so that's fi of x, and then it's like gi of x is just the same thing but with the cosine. So cosine of x omega vector, it's I over there. And so your new capital X would just be given by this thing. It's just f1x, then g1x, and then f2x and g2x and so on. And yeah, that's your Fourier basis. And we can do this, we can certainly do this because of the existence of Fourier transform. So yes, this is completely valid. You can certainly be doing this. There's no issue with that. Then you have something called multicollinearity. So this is like the Fourier basis, by the way. Another thing is multicollinearity. So I told you that you should not apply linear transforms, linear basis functions, and then keep the old function, the old feature, right? Because that's gonna give you some problematic things. The reason for that is, well, x transpose x could have its determinant equal to 0. So remember that we get the best theta as x transpose x inverse x transpose y, right? This is the best theta value possible. So if your x transpose x is not invertible, that is to say that the determinant of x transpose x is 0, then things are messed up. Now it just so happens that because for any theta, more like for any vector v, in fact, your v transpose x v is bigger than or equal to 0, and like equality only happens. So if this is like equal to 0, y, and equality only happens if your xv is equal to 0. That is to say that v is in the null space of x, right? It is basically, this is just because x transpose x is a positive definite matrix and all that stuff, but whatever. So it's just a trivial property that if this is equal to 0, then this has to be equal to 0, and it just so happens that otherwise this thing is never 0, right? Otherwise this thing is certainly, so else v transpose x v is strictly bigger than 0. So if xv is not equal to 0, then that implies that x transpose xv is also not equal to 0, because if it was, how would this even make sense? So what that means is that this condition is actually equivalent to this condition, right? Yeah. So this not being invertible just means that, well, x is not invertible. That is to say, x has linearly independent columns, and that should not happen. That only happens when something stupid is being done with linear regression. So just be aware of that. So one way to solve this is to do something like this: x transpose x plus something like mu I inverse x transpose y, and this quantity is actually like always full rank. So this matrix is always full rank, and that's because for any vector v, x transpose x plus mu I times v transpose over there, this quantity is always bigger than 0. Yes, strictly bigger than 0, and that implies that x transpose x plus mu I v cannot be equal to 0 for any v, right? And that means there's nothing in the null space of x transpose x plus mu I, and that implies this will always be invertible. Now this whole formula, it looks like it's coming out of thin air, right? Like, why did I just put a mu I over there? So one thing you could do is just set mu to be like incredibly small, so that like numerically you can solve these things, but then it doesn't make all that much of difference really. Another thing you could do is actually use this formula, which is to say, find something that actually uses this formula, and that something is called ridge regression. So let's just get into it. Let's get into what ridge regression is. Yeah. Oh, before that, I should probably also mention that another way to be avoiding this is to do something called the principal component regression, where it is like you just do PCA on your capital X data, and using the transformation matrix that you get from that, you transform whatever input the X test data set you'll be given, and then you predict on that instead, right? And so that's called principal component regression. And this problem that you're facing is called multicollinearity. Cool. Now let's get to ridge regression, which solves this issue and also solves another issue, in fact. So the start of ridge regression is not like to solve multicollinearity. Instead, the way it starts off is different. So linear regression is like also prone to overfitting sometimes, right? I mean, every model is, in fact, like sooner or later it will overfit. And so it just so happens that whenever it overfits, there's a certain pattern that we observe. That is that the magnitude of your theta vector, this is actually like really large, is large when overfit happens. So this is a symptom of overfitting. So what we can do is like avoid this, and that will sort of avoid overfitting as well. And the way we do that is we put a penalty for whenever your theta becomes too big. And so the way it's done is like you have the usual loss function y minus x theta squared, but you also put a penalty for your theta being big. And so this is your new cost function. So just by the way, a loss function is something that's for a single data point, and a cost function is for the whole data set, but I'll be using them interchangeably in any case, so don't mind. But yeah, so I'm just gonna call it as L theta. So now we want to minimize this function instead. So once again, we just like figure out what the nabla theta L thing is. So this part is pretty much the same as before. We can just kind of like copy everything, right? So it's just this quantity. Yeah, but this part is different. So it's just minus 2 mu theta essentially, right? Yeah, so that's what nabla theta L is. Now we can use this, we can set this to equal to 0, and that will give us the theta hat thing. So just recollecting all of this, we just get like minus 2 x transpose y, and then plus 2 x transpose plus x, sorry, x transpose x, plus, why is this minus? Did I mess up somewhere? Oh, sorry, you should be putting a penalty, so it should be a plus. It's a loss, it's not, yeah, sorry. So this should be positive over there. So now it's going to be like plus I mu, that is of theta, right? And now setting this to 0 gives us theta hat is equal to just what was I going to do though? Yeah, this thing, x transpose x plus I, so mu I inverse x transpose y. That is just Ridge regression. So this penalty is sort of arbitrary, isn't it? Like, you could have used any other norm. You could have used the L1 norm for all you know. Well, you can, and apparently what that gives you is another thing which is called lasso regression. And no, lasso regression does not have a nice analytical solution like this. Instead, you have to do something like gradient descent. In fact, you can't even do gradient descent because it's not continuous anymore. So instead, what you do is something called the coordinate descent, and it just so happens that when you do that, most of your features are selected out, as in the features that are not so important. Well, lasso regression doesn't optimize it optimize using those features anymore. So whenever your theta I is 0, your theta is 0 forever, essentially. Yeah. So lasso regression is just basically like L theta is this quantity yeah right, and so that's lasso regression. Now this could be generalized, and this is called regularization. And when we generalize this, you should essentially be using this expression at your loss of theta, so regularization, or more like L1 by P regularization. So you used like the L2 norm, L1 norm. What if you use L1 by P norm? So in that case, what you would be doing is just L theta is once again the same stuff, y minus x theta squared, but now you're doing plus mu times of the L1 norm of this guy, so just that, so L1 by P norm, right? And it turns out that the bigger the p value is, the sparser your number of features for like final like prediction actually become. So when I say sparser, I mean like lasso regression just selects out most of the features, right? Well, apparently if you do L1 by 2 norm, it selects out even more features. And so eventually, like, as p approaches infinity, we just get L0 norm, and L0 norm is just the number of non-zero entries in your vector, right? So it just tries to minimize that, and you can guess what's going to happen. It just tries to have as less features as possible. And so yeah, this is L1 by P regularization. Cool. And yes, most of these are optimized using coordinate descent and not gradient descent. So coordinate descent is like you have a point in your feature space, and you take a bunch of random points in a sphere around, and then you figure out, okay, cool, this point is probably giving us the best gain, so we'll just move around that, right? Yeah, no need for calculating the gradient or whatever. That's what coordinate descent is. So far we have understood linear regression, decision trees, Ridge regression, lasso regression, regularization. Let's go to something called gradient descent, right? So at this point, I should mention what a convex function really is. Like, we sort of already know what a gradient is, right? Yeah, we used it, obviously. So a convex function is something which looks like a cup. Yeah, a more formal definition is something like this, that f of so if it's a scalar function, then it's like f of alpha x1 vector plus 1 minus alpha x2 vector is strictly less than, so not strictly, is it? It's less than or equal to alpha f of x1 plus alpha plus 1 minus alpha f of x2, right? Where x1 x2 are just points, right? So like graphically it looks something like this. You have x1 over here, x2 over there, and then this value is what so like this whole thing is what this quantity is, but then this whole thing is what this quantity is, right? Yeah, so that's a convex function. And in fact, from this thing, so by the way, alpha should just be, alpha is in 0 to 1. I kind of forgot to mention that. So from this, I should probably write it down, convex functions. From this, it's actually not that hard to show that, like, for a single variable convex function, this is equivalent to saying that f double dash of x is bigger than 0. But, well, whatever, I'll leave that to you. Next. So what's the benefit of a convex function though? Why did we even like discuss this? The thing is, since a convex function always has this sort of, what is it actually going to say? Yeah, always has this increase in gradient sort of nature. Then what we can say is that it will only have one minima. Yeah, it won't have multiple local minima, and that avoids the whole problem that neural networks in many other models face, that they get stuck in one particular minima, right? Oh, so another like important thing is like ensemble methods get rid of this whole problem of being stuck in one minimum, because obviously, like, you'll be having multiple different models starting at multiple different locations, so they will have different minimas that they reach. Okay, anyway, so that's the convex function. Right, now gradient descent is actually not that hard to understand. All we're doing is like we're just updating theta according to this thing. So theta t plus 1 is just equal to theta t minus alpha, the gradient with respect to theta of L at that particular theta t value. Right? That's all you're doing. This is a gradient descent. Really, like, people make so much fuss out of this, but it's just that simple. You descend along the steep, along the path of highest ascent, which is the gradient. Pretty obvious, because you have d theta equal to nabla theta L, sorry, dl. That times of theta transpose, right? Okay, just take a dot, in fact, d theta vector. So, like, obviously your dl is like maximized whenever your d theta is in the same direction as this vector, and so that's the direction of the steepest ascent. So if you descend along that, your dl is the least possible, right? And it's obviously negative, so highest magnitude but in negative. So yeah, so that's what you do. That's what gradient descent is. Now there's another variation of this. It's called gradient descent with momentum. So in that case, what you do is like theta t plus 1 is equal to theta t minus alpha and something that they call pt. So pt is momentum, and pt is actually updated according to this rule. Yeah, I know, it's weird, isn't it? So essentially what you're doing is that you're thinking that your gradient is not your velocity, but instead it's your acceleration, if that makes any sense. But I'll just leave it at that. You figure out the physics later. But yeah, that's gradient descent with momentum. Another important variation is something that's called mini batch gradient descent. So a mini batch gradient descent is something where, usually in gradient descent, what we do is that we can compute this quantity, gradient with respect to theta of L, for the whole batch. So like for the whole data set. So L is something that's computed for the whole data set, and then you just compute theta like that. But for MBGD, what you do is that you split a data set into small equally sized data sets, and then you compute the loss for this, and then you do this quantity computation, and then you do like some updates. So maybe you do like 3 updates with this, I don't know, whatever you do, and then you move on, you update with this, and then you update with that, and so on, and then you just keep repeating. So maybe this is like one update. I think so. That's the way it is done, most likely. Actually, no, I don't think it's one update. It's like so the number of epochs, right, that you want to be running this. Yeah, I guess so. But okay, that's actually probably not a good idea. So just say one update. Fine. One update. Cool. So just like do this, and then you do this like epoch times. Something's wrong with this. Oh yeah, okay, so epoch times. So let's just say this has n dash size, so epoch n dash size. Now, of course, like you could have a different sort of way of whatever. We don't really care about this. Yeah. Yeah, I guess this is correct. I think so. Anyway, so E is just the number of epochs. So an epoch is just the number of times that you have seen. So one epoch is like one. How do I say this? So whenever you say like one epoch has passed, it means that we have seen the data set, whole data set, from start to finish one time, right? That's like mini batch gradient descent. Now this taken to an extreme scenario is something that's called stochastic gradient descent, where what you do is like you have a data set and for each data point you do one update, right? So your batch is just a data point at this point. So SGD is just MBGD with n1 equal to 0. Sorry, n1 equal to 1, right? 1 like n dash. Yeah, that's SGD. So an important thing is that SGD is an unbiased estimator of the actual gradient. So an estimator is once again just something that estimates the true value of something, right? So over here what you're doing is like for each data point you are getting some gradient gi, right? And you're updating according to that. So by the end what you have done is that you have updated according to this thing, summation of gi alpha, right? That's by how much you have updated in SGD. Okay, negative of that, but whatever, in SGD. Now what we are seeing is like the summation of alpha, so in SGD for n iterations. Now in case of just updating directly, like for normal vanilla gradient descent, you once again trying to minimize the MAC, right? So the loss L is just MAC, so then your gradient with respect to theta of the loss, that's actually like 1 upon n summation of this quantity, right? That's a good estimate for the gradient at some point like in between of that n cycles, right, of n iterations. So it would be something like this and that times of n. So for n iterations, okay, actually no, it's this thing. So minus alpha, yeah. So you can sort of say that approximately this is the update that you did for theta, right? And so obviously these are actually the same thing, right? Okay, this actually has to be this times of n, because because you have done n iterations, so minus n times of this guy. So obviously these two are the same. So what we are essentially saying is that the bias for the true gradient, so this thing is actually just call it as G, which is actually the expected or more like the average value of the, I shouldn't say expectation, that sounds like probabilistic stuff. So the average value of the the estimated gradient, right, minus what the true gradient is. That's what the bias is, right? Yeah, so in this case it's just 0 because it's just minus alpha summation of gi, and then we are saying it's minus, well, it should be actually sort of an approximation, but well, whatever. So minus approximately minus alpha gi, so minus alpha summation of gi, and that's like 0. So yeah, you could say that in a way SGD is an unbiased estimator of the actual gradient. But I sort of find this funny, like you're already taking an approximation and then you're saying that this is equal to 0, so we should be just saying bias is approximately 0, right? Yeah, cool. So that's SGD. Anything else that I wanted to say? Well, this is pretty much it, I guess so. So I'll see you guys in the next video. Bye.